Hi, my name is RIZA. Now I will begin this presentation with the details of our fermented product, cheese. Starting with the definition. Cheese is a fermented dairy product made by coagulating milk proteins, primarily casein. This coagulation process is typically achieved using acids or rennet enzymes. Moving on to the fermentation process. Fermentation involves lactic acid bacteria that convert lactose into lactic acid. This acidification causes the milk proteins to coagulate and form curds, which is a key step in this cheese formation. Next, let's talk about the microbiomes involved in cheese production. First, we have lactic acid bacteria or LAB. This includes Lactococcus, Lactobacillus, and Streptococcus species. They play a crucial role in fermenting the milk by acidifying it and helping form the curd. Then we have molds. For example, in blue cheese, molds like Penicillium species are introduced to develop unique textures and flavors. Lastly, yeast. These microorganisms are important for the fermentation of certain specialty cheeses. Now, let's take a look at the types of cheese and the microbes involved in each type. Starting with cheddar. Cheddar uses lactic acid bacteria such as Lactococcus lactis, Lactobacillus species, and Streptococcus thermophilus. These bacteria are crucial for acidifying the milk and aiding in curd formation. Additionally, Propionibacterium is sometimes used in Swiss-style cheddar to create the characteristic holes or eyes in the cheese. Next, we have brie. Brie also uses lactic acid bacteria, specifically Lactococcus lactis and Lactobacillus species. What sets brie apart is the mold Penicillium candidum, which forms the cheese signature white ring. Moving on to parmesan. Parmesan relies on lactic acid bacteria like Lactococcus lactis and Lactobacillus helveticus. Some specific parmesan variants, such as Swiss style, also incorporate Propionibacterium for texture and flavor development. Lastly, we have blue cheese. Blue cheese uses lactic acid bacteria for fermentation, such as Lactococcus lactis and Lactobacillus species. But what makes it distinct are the molds Penicillium roqueforti or Penicillium glaucum, which give the cheese its famous blue veins and unique flavor.
Hi, my name is DANISH, and today I will present the detailed process of cheese production flowchart in context of mozzarella. The first step is milk resorption, standardization, and pasteurization. The fresh cow milk is collected and standardized to adjust the casein to fat ratio, optimizing cheese yield and texture. The milk undergoes high temperature, short time HDST, pasteurization at 72 Celsius for 15 to 20 seconds to eliminate pathogenic microorganisms while preserving the milk proteins. The post-pasteurization, the milk is cooled to 37 Celsius. The optimal temperature starter for the culture inoculation. The second step is production starter cultures in bioreactor. The selected lactic acid bacteria (LAB), including Streptococcus thermophilus and Lactobacillus delbrueckii, are propagated into the stirred tank bioreactor (STR) under controlled pH, temperature, and anaerobic conditions. These bacteria ferment lactose into lactic acid, which acidifies the milk and facilitates the coagulation. The culture inoculum is then concentrated, freeze-dried, and refrigerated before being introduced into the pasteurized milk. The third step is inoculation milk with starter culture. The starter culture is added to the milk at 2% inoculation rate. The LAB metabolize the lactose, producing the lactic acid and reducing the milk pH to approximately between 6 to 6.2 pH. This controlled acidification is critical for subsequent enzymatic coagulation. The fourth step is enzymatic coagulation, which is the addition or with rennet addition. The rennet containing the enzyme chymosin, which is the animal-derived or recombinant, is introduced to cleave the casein, destabilizing casein vessels and forming a gel matrix. Coagulation occurs between over 30 to 45 minutes at 37 Celsius, resulting in the formation of semi-solid curd. Next, the fifth step is curd cutting and whey separation. The coagulated milk is mechanically cut into 1 to 2 cm cubes to increase surface area and promote whey drainage. The curds are gently stirred and heated to 42 Celsius to further the expel whey and enhance the curd firmness. And then, the sixth step is the acid development and optional cheddaring. Discontinued LAB activity reduced the curd pH to 5.4 to 5.2 pH. Some mozzarella variants undergo cheddering, where curds are stacked into additional weight and develop acidity, which is essential for proper curd stretchability. The seventh step is stretching, which is into the pasta filata process called. The curd is then immersed in the hot water between 80 to 85 Celsius to achieve plasticization. At pH approximately 5.2, the curd is mechanically stretched and kneaded. It aligns protein fibers to produce mozzarella characteristic elastic texture. Then, for the eighth step is called molding, cooling, and braining. This stretch the curd is shaped into the final forms, which is in forms of balls, block, or logs, and submerged into a cold brine solution, which is a 20% sodium chloride at 8 to 10 Celsius. Braining enhances the flavor, surface texture, and shelf life. For the next step is called packaging, which is this step. Mozzarella is packaged in a vacuum sealed pouches or brine-filled containers depending on the product type, fresh or low moisture. Packaging ensures microbial stability and moisture retention. And the final step is cold storage and quality assurance. The finished product are stored at 0 to 4 Celsius. This quality assurance includes the pH monitoring, moisture, salt analysis, and microbial testing to comply with safety and quality standards. This image summarizes the traditional cheese-making flow, highlighting the key stages like milk, fermentation, coagulation, curd handling, and ripening, which it emphasizes the cyclical nature of steps such as cutting, stirring, and molding, which are the foundational to the cheese production. This is the PNID of the cheese production making. This diagram illustrates the equipment and workflow in a mozzarella production facility, likely designed using the software SuperPro Designer. As you can see, the main component here is one of the bioreactor, stated as BR101, is for a starter culture production, and pasteurization is on the PZ101, and cooling is on HS101 for milk treatment. Stretching, BX101, and molding units is for curd processing, as this PNID provides a technical blueprint of how materials move through each unit operation to ensuring efficiency and scalability.
So let's talk about cheese vats. They're the most commonly used bioreactors in cheese production. Now, a cheese vat's a large specialized vessel used to facilitate the fermentation and formation of cheese by storing milk, curd, and whey. They enable batch fermentation via bacterial action. And these cheese vats, much like any other bioreactors, provide the optimal condition for bacterial growth, enzyme activity, and curd formation. Most cheese-making industries have either a round vat, double O vats, or oblong cheese-making vats. These vats are also designed to be open vessels, closed vessels, be it vertical or horizontal in orientation. Oftentimes, cheese vats are also dynamic in their design, as cheese-making industries make changes and additions in vat designs to improve yield and enhance fermentation efficiency. Now let's talk about what makes it special. In cheese-making industries, cheese vats and their processes are often automated, making the quality of cheese produced consistent. This coincides with the cheese vat's ability to diversify and increase the agitation efficiency up to curd formation. In addition, its simplicity in process control and cleaning allows for a more constant and effective fermentation, which also coincides with its flexibility in cheese production. Should there be any minor issue that comes up during production, these parameters can be automatically or manually adjusted to rectify or further increase the product's yield. On the other hand, these vats are often expensive in installation. Therefore, the initial costs of setting up and powering a cheese vat are often expensive. As mentioned before, these vats are large and they take up a large space to function ideally, and sometimes lack of proper maintenance may introduce contamination to the product. Moreover, these vats are specifically designed for cheese fermentation, making it less versatile than a bioreactor.
Hi, my name is IRDINA. Modern mozzarella production is being transformed by artificial intelligence. First, the AI touchscreen dashboard displays real-time data like pH drop, temperature trends, and curd firmness predictions, helping operators make quick, informed decisions. Artificial intelligence is transforming mozzarella production. Computer vision models like CNN and vision transformers can detect ripeness by analyzing texture, color shapes, and surface defects, replacing manual inspection. Real-time camera system monitor cheese blocks on the line, checking moisture, softness, and shape consistently. Machine learning models predict proteolysis with 92% accuracy, allowing producers to optimize shelf life, release timing, and storage. With hierarchical AI, ripeness is classified based on temperature, pH, and microbial activity. AI doesn't just assess quality, it helps control fermentation, ensuring every mozzarella batch stretches, melts, and tastes exactly as it should. Next, the AI integrated bioreactors features a digital control panel that monitors fermentation conditions such as pH, temperature, and viscosity. Sensors and automated storing paddles ensure a precise, sterile environment for consistent curd quality. Optimizing fermentation and mozzarella production starts with advanced bioreactors. AI-integrated control panels process real-time data from built-in sensors and computer vision systems to adjust pH, temperature, and texture during fermentation. Microbubble oxygen infusion boosts microbial activity, while automated curd cutting ensures precise timing. Hydraulic setting vats allow exact control of enzymatic and microbial action, improving curd consistency. Electropolish churners improve mixing and heat transfer. Clean-in-place systems maintain hygiene and batch reliability. Finally, cooling and brining vats stabilize the cheese, remove excess moisture, and prevent microbial shift, ensuring every step after fermentation supports the highest product quality. Finally, advanced bioreactor or cheese vat designs now include microbubble oxygen infusion, improved mixing paddles, and automated curd cutting, boosting efficiency, accuracy, and overall cheese. Genetic engineering improves mozzarella production by using safe hosts like E. coli, Pichia pastoris, and plants to produce recombinant chymosin. These systems boost milk clotting efficiency while supporting eco-friendly, animal-free cheese making. When combined with optimized fermentation conditions like pH 6 to 7 and temperatures between 35 to 40 degrees Celsius, enzyme activity is maximized. This leads to better curd formation, higher yields, and improved texture, ensuring consistent, high-quality mozzarella.
Hi, my name is FATIMA YUSMALIZA binti Muhammad RIDZUAN. So now I'm going to quickly walk through the essential safety and good manufacturing practices or GMP in cheese production. Adhering to these guidelines is crucial for ensuring product quality and consumer safety. It all begins with meat reception, standardization, and pasteurization. Here, we must ensure meat comes from certified healthy cows, and personnel wear gloves, hairnets, and clean attire. Pasteurizers need regular calibration and cleaning. Next, for the production of starter cultures, maintaining sterile bioreactor conditions is key along with monitoring pH and temperature. We also use high purity strengths and sterile handling techniques. Moving on, in the curd cutting and waste separation stage, it is vital to use stainless steel and food grade cutting tools and to sanitize equipment before and after use. During acid development and optional cheddaring, we accurately monitor pH with calibrated device and maintain proper hygiene during manual curd handling. For stretching or the pasta filata process, clean temperature control water is essential and personnel should avoid direct hand contact with curd. Finally, for molding, cooling, and brining, brine must be filtered and its concentration monitored, and cooling water must be portable. Packaging happens in a clean room using food-grade vacuum seal or brine-tight packaging. And for cold storage and quality assurance, a consistent 0 to 4 degrees Celsius temperature is maintained, with regular checks on microbial load, pH, and salt or moisture. Following these GMPs ensure safe, high-quality cheese. Now, let's look at the HACCP or hazard analysis and critical control points for our cheese production process. This table outlines the key steps, hazards, and corrective actions needed to ensure food safety. We start with meat pasteurization, which is a critical control point to eliminate pathogens. The milk must reach 72 degrees Celsius for 15 to 20 seconds. If it doesn't, it's either reprocessed or discarded. Next, during starter culture handling, the main concern is biological contamination. Although it's not a CCP, aseptic techniques and proper lab hygiene are essential. For renal addition and coagulation, pH must be between 6.0 to 6.2 to avoid improper coagulation. pH adjustments are made as needed. In the stretching process, both acidification and temperature are monitored. The pH should be between 5.2 and 5.0, and the temperature between 60 to 85 degrees Celsius. Brining is not a CCP, but microbial growth is a concern. Salinity and temperature are monitored daily. Packaging is a CCP due to the risk of seal failure. Packages are visually inspected and repacked if needed. Finally, in cold storage, the temperature must stay between 0 and 4 degrees Celsius with continuous logging to prevent pathogen growth. That's all from me. Thank you.